I want to talk about unit vectors. So we talked about those unit vectors in R3 and R2. And it turns out that these unit vectors are pretty important vectors to deal with. Because they serve as what they call a basis vector. And so any other vector in that space or in the plane can be written as something times one vector, one of these basis vector, plus something times the other vector. So whether you use a hat or an arrow, we want to make sure that the I and the J are bold-faced. And then, oh, it's the other way, 1, 0, right? And then if you're in 3D, then you have 3 of these vectors. So the I, J, K. And we define the I to be 1, 0, but that's the I if it's in 2D. If you're in 3D, in R3, then the I has to be defined a little bit differently because there's 3 components. So we want to just make sure that we fill in the components that we need to fill in. Okay. So there's also another interesting thing with unit vectors, or the idea of unit vectors. And for us to think about, if you have a vector v, and then for some reason, we might be interested in one of these reasons sometime today or tomorrow, that we want another vector that's going in the same direction as v, but have it at a specific length. Let's say the specific length is 5 or something. So one would think that if you just want the vector going in the same direction as v with a length 5, you would just multiply this by 5 times v. But do you see how that might not work out? Because what you're going to get is a vector that's 5 times as long as v, but if v is like 3 units long, then now you have a vector of 15 units long. So for us to be able to deal with that, what we want to do is we want to do something called normalize the vector. And the idea behind normalizing the vector is to get it so that it's unit length, so that we can deal with a problem like this where we can just multiply by the number that we want the length to be. So we normalize the vector by taking a vector v and then dividing it by its magnitude. Oh, did I talk about magnitudes? No. So a magnitude Remember, a vector has a direction and magnitude. So what was the magnitude? It's really the length. So it turns out that if you take a vector and you scale or multiply it by 1 over the length, or essentially divide by the length, then it becomes a unit vector. And what we can do is just do a simple example and see how it works. So let's look at a vector in 3D. 1, 2, 3. How do you find the magnitude of a vector? So the magnitude is the length. The length is the distance between the head and the tail. And if you put this vector in standard position, it's like finding the distance from 0 to whatever the point that this thing points to, right? So it's essentially these numbers minus, each of them minus 0, square them, add them, and then put them under a square root. Yeah?
So it would be like the thing we did with the box, where it's the box would be origin and then the length would be the diagonal?
Yeah. So it's like the diagonal of the box. Derivative. There's no derivatives here.
I mean, it's a different version.
It's a yeah. It's essentially the distance formula.
I was using derivative in the other.
Oh.
Derivative.
Yeah. No. Careful how you use derivatives in calculus. Hello. 15? Square root of 15? Yeah. I'm trying to undo. Let's not do decimals. Let's just keep it at that. 14? So I had put 13. You guys said 15. If we were in the stats class, would be good. Okay, so if we want this vector to have length 5, then we would just consider this vector v and divide it by its magnitude. Well, anyways, the vector v divided by its magnitude is going to be unit length. And unit length means it has length 1. And so if it has length 1, then this idea of scalar multiplying it, scaling it by 5, just means you just multiply it by 5, and then you've scaled that unit vector into length 5. And then that's it.
How do you divide the top by bottom?
You can do it. I mean, you can write it like this: 1 over square root of 4. I mean, you can write it. Let's.
It's like 1 over square root of 14.
Yeah.
2 over.
Let's go through all the different looks here. So technically, we don't have scalar division. We have scalar multiplication, but division is like opposite or the reciprocal, multiplying by the reciprocal. I got asked that question in Math Jam, by the way. In algebra, why when you divide, why do you always think about the reciprocal? I have to go through the whole process about the inverse operation. So we think about division as opposite or the multiplication of the reciprocal, and then You distribute this like you would do a scalar multiplication. Frederick, did you have something to say?
As we work on finding the direction of that, just do the hat over and see the vector and the direction.
Yeah.
So instead of doing the actual vector over the vector, what do we have?
Yeah, make sure you write it clearly. The hats and the arrows might look alike, and so. But I'll only yield to physics notations for so long. In fact, I was in a meeting with Professor do you guys know Attila Alteto? He said one of the things that we're talking about, and Professor Partland was there too. So what do you guys want from math people? And Attila said, don't talk about physics and math. I said, oh, gladly. All right, where are we? So finding the length. So this is a unit length. If you were to take the magnitude of this, you'll see that the magnitude is going to equal to 1. And so now to find vector in the direction of v with length 5, then I just need to multiply this whole thing by 5. So I can just say 5 v over magnitude of v, or if I do all this work, I can put in the 5 wherever it's appropriate, or finally get 5 over root 14, comma 10 over root 14, comma 15 over root 14. Okay, so if you were to take the magnitude of this, which is to, take each component, you square it, add them up, and then take the square root, you should get 5. Okay? All right, now let's jump to this idea of the dot product. So definition of the dot product. There's actually a couple ways to define this, and depending on what book you're using, they'll define it one way and then say the other way is a result of the definition. I like to consider both of them as definitions. They mean the same thing. We can go through some arguments about how one works geometrically and one works algebraically, but I'll just call them both definitions. So I'll put the algebraic definition and the geometric definition of the dot product in 2 or 3 dimensions, or 5 or 7 dimensions, whatever dimension you need to be in. So A and B are vectors. The dot product will be the product of the components, component by component, and then you add them all up. Now, if you look at this dot product carefully, look at the algebraic definition, or you can even look at the geometric definition of the dot product. If you look at these definitions carefully, what can you notice about the result of this dot product of 2 vectors? The result's a scalar, right? And that's an important fact to remember. So depending on what you look at, you don't get a vector anymore. You take 2 vectors, you do something to it, and then now it's not a vector anymore. And that's kind of significant. A lot of times this is known as the scalar product. Specifically because the result turns out to be a scalar. So we multiplied a vector by a scalar called scalar multiplication. We get a vector, and now if we try to multiply two vectors together, we get a scalar. So this is a scalar. So we'll see in the next section that there's going to be another operation where we multiply two vectors, and I say multiply in quotes. We multiply two vectors together that we would get another vector. And we'll refer to that as a vector product, but for now, let's worry about this product, the scalar product. So one of the examples that I usually like to use for the dot product is an example in higher dimensions. And I actually use the dot product to compute your grades. So each person is going to be assigned a vector, and that vector will be your average scores of your quizzes, your exams, your homework, your labs, and all that stuff. So I'll put that in a vector, and then I have another vector multiplier that describes the weights of each of those categories. By taking the dot product, I'm going to get your final grade. So let's take a look at that example. And then we'll focus a little bit more on the geometric definition after that. So this does not have a geometric definition, but it's just an example I like to use. Let's call the first vector W, vector W. And these are the weights of each category in your grade. Do you guys remember? Does anybody have their syllabus handy? Or we can just make it up?
Quiz is 10%.
So we'll start with a quiz. That's 10%.
Homework is 15%.
Homework is 15%.
Labs are
5%.
The midterms, all the midterms combined are 40%.
Are you making this up now?
No, and the final's 30%.
Does this add up to 100?
Yes. 30 plus 40 is 70, 5 plus 15 is 20, that's 90 plus 7 is 100.
Okay. All right, let's pick a student. Anybody want to volunteer? We're only volunteering your name. Lorenzo, how'd you do with your quizzes? Give me a score between 1 and 100. 70%. How about your homework? How did you do?
Oh, I did a lot of homework. I guess, what do you,
95 or 100? 100, wow. How'd you do in your labs? It's easy, 100. Oh, how'd you do on your exams?
not applicable.
No, let's pretend applicable it. 80, wow, good job. How'd you do on your final?
70.
50, come on. So this is Lorenzo's vector. Perfect student would get hundreds, right? Oh, I've had perfect students before. Right, Caleb? So, if I'm interested in finding out Lorenzo's final score, I would dot these two vectors. So, W dotted L, and then now I just do the computation. So I'll write this out. I don't know why it's so long. And somebody punches this in the calculator and tell me what I get, I can give him his grade. I use Excel. It goes a lot quicker. You're going to say 80? 93.2? Can everybody verify that? Just one more person to verify. Got 80? So I got like 3 or 4 people say, I'm going to go with 80. All right, Lorenzo got a C+. Oh wait, is that a C+? Okay, you got a B-. That's good. So that's it. It's a simple application of a dot product. And also it's a dot product of vectors that are larger than 2 or 3. So we're talking about 1, 2, 3, 4, 5. We're talking about something in R5 now, 5-dimensional vectors. All right, let's go take a look at the geometric definition of the dot product. So the geometric definition of the dot product actually is most useful if you know the algebraic definition of the dot product, because a lot of times you would be interested in finding the angle between them. So let's take a look at this geometric definition again. Let me copy this on another page so that we can have it right next to us. And basically, if you draw a vector in 2 dimensions or 3 dimensions or 5 dimensions, if you can somehow define an angle between them, and we would generally be looking at the smallest angle between them, the angle between them is theta. It turns out that the cosine of theta has this play with the dot product. Yeah.
You said it's small, but isn't it the angle between the direction that they're going, not the head in one and the tail of other, whereas that might be bigger.
Well, no, they have to be tail to tail, and if you look at any 2 vectors that are tail to tail, there's like 2 different vectors to 2 different angles to look at.
That was just confusing. From one example.
Oh, yeah. So it's the smaller of the 2 angles between them, and if it's if it's a line, if it's like 180 degrees, then it'll be 180. So it turns out that this is a useful formula if, again, if we know how to find the dot product algebraically. We can find an angle between 2 vectors by computing the dot product and dividing by the magnitude of each of those, multiplying the magnitude. So this geometric definition of the dot product becomes a little bit more handy when you need to find the angle between a couple of vectors. Or when you need to find an angle between 2 things, and if you can somehow define vectors that define those 2 things, then that's the angle that we're looking at. So this kind of brings me to a problem that I had when I was in college. I was in this advanced linear algebra class, and they asked me to find the angle between a side of a cube and its diagonal. And, I computed it this way, and then I doubted myself, and then I said, no, it's got to be 45 degrees, right? But no, it wasn't. So if you're looking at a square, the angle between an edge of the square and its diagonal is 45 degrees. But if you look at it as a cube, it's no longer, oops, I lost my perspective here. If you look at a cube, the angle between, I can't see the edge anymore. Let's try to, I know what. Still right-hand rule work? So that's my cube, and then the diagonal would be from maybe the origin to the opposite vertex, and then one of the sides would be just one of the edges. It turns out that that's not 45 degrees, so I ended up getting that problem wrong because I didn't stick with my gut. All right. So how would we do this? The cube can be any size we want, so as long as they're all the same side. So let's assume that the cube goes from 0 to 1, or we can assume it goes from 0 to c. Z, C, S, C, cube. So one of the edges for the cube would be the vector 0, 0, c. And then what would the diagonal of the cube be if the cube is like pushed against the origin? You understand my question? Are you guys with me? Am I just talking shit? I mean, talking. A cube. CCC. So if the cube goes as far as c units, then they're all going to have c units in the x, c units in the y, and c units in the z. And so to find this very opposite part of the cube, the diagonal, away from 0, 0, 0, you have this vector c, c, c. Or 1, 1, 1 if it was 1, if it was a unit cube. But we can make it generic to let you know that it really isn't going to matter. All right, so that's like your A and your B. If you want to find the angle between these two vectors, the edge and the diagonal, then you just dot them, you take the magnitude of each of them, and then you take the cosine inverse. So let's put it into the formula. What?
So for the cosine theta, it's called A hat, B hat, right?
Yeah, so I was just going to write this whole thing down. So 0, 0, C. So that's the edge dotted with the diagonal divided by the magnitude of each of them. By the way, they use double bars in the magnitudes for the magnitudes. Let's pause for a moment for this idea of this magnitude. The magnitude of a two-dimensional vector is the square root of a squared plus b squared, right? It's the square root of each of the components. And then for R3, it's just the square root of each of those squared, and then you add them up. Now, if you're in R, just the real numbers, and follow through the same thought process of a magnitude. So the magnitude in one dimension So the magnitude in one dimension would be like the distance between the origin and that point. And so if we want to think about that, the magnitude of 3 is really the square root of 3 squared. It is kind of important that, you know, the squared is first and then you take the square root, because when you square a number, what do you get? It's going to be positive, right? And when you take the square root, you'll undo it, and then it'll be positive. And that would work. The magnitude of negative 3 will also end up being 3. My point is that the magnitude in one dimension is really the absolute value. Okay? So what I want is essentially permission to, instead of doing the double bars for the magnitude, if you see single bars applied to a vector, it means the magnitude. All right. Now that we got that out of the way, let's take the dot product of the numerator, 0 plus 0 plus c squared. Now let's find the length of the denominator. So that's c. The length of CCC, I think it's 3 square root of c. C square root of 3. Right? So c squared, c squared, c squared. You factor out a c squared out of the square root, it just becomes a c, and then you have 1 plus 1 plus 1, which is 3. And then you have c squared on top, and you have c squared in the bottom, and you have 1 over square root of 3. So it really didn't matter what c was equal to. C could have been 1, c could have been 15. Your angle, or the cosine of the angle between them, is 1 over root 3. And now the cosine inverse of 1 over root 3 so this is a time when you probably might be interested in going into degrees instead of radians, just so your result looks like it's in degrees and it's understandable. I mean, you can keep it in radians also, but 54. Let's go at 54 degrees. So it's bigger than 45 degrees, bigger than this diagonal business. And then, yeah. Any questions? I think there were some c's that canceled, and then that just left with 1 on top and square root of 3 in the bottom. What? What? Oh, here? From here to here? It's the square root of c squared plus c squared plus c squared. So that's 3c squared, and then the c squared under the square root becomes a c. Okay. All right. Now, if you look at the formula again, the magnitude of A and the magnitude of B are always going to be positive. So the cosine could be positive or negative, right? And so the dot product could result in a positive or negative number, depending on the angle between them, it turns out. So you could tell that if the angle theta is between 0 and pi over 2, I guess we should look at the cosine graph. It's also good to know the domain and range of the arc cosine function. So you can only put in angles that are between 0 and pi, or you can only result in angles between 0 and pi. And that's this whole business about making sure that it's the shortest, the smallest angle between the two vectors. And it turns out that if your angle is acute, then the dot product, the cosine of theta is going to be positive, and therefore the dot product is going to be positive. And if your angle is obtuse, then the dot product will give you a negative value. So that would be good to try to remember when you're taking dot products of things. If you take dot product of something, you get a negative number, that's okay. That just means that the angle between those two vectors is greater than 90 degrees. Okay? Any questions about dot product so far? All right, let's take a look at one special property and then a whole slew of other properties. And this special property is, again, based on that geometric definition of the dot product. So the whole idea of the dot product being positive, well, let me check my inequalities. Oh, sorry, I need to take something out here. So these inequalities say that if it's less than 90 degrees, then it's going to be positive. If it's bigger than 90 degrees, it's going to be negative. So right exactly at 90 degrees, it turns out that it's going to have to cross 0. That's like the intermediate value theorem, right? I saw a little cartoon that says, why did the chicken cross the road? And then the road was like, never mind. Chicken. Road. XY. So why did the chicken cross the road? It's because of the intermediate value theorem. Yeah. All right. Okay. Two vectors are orthogonal if and only if the dot product's equal to 0. So this is that one very special angle where the cosine of 90 degrees is equal to 0. So because the cosine of pi is equal to 0, 90 degrees, 90? That's pi over 2. So because the cosine of pi over 2 is equal to 0, and that's part of the dot product definition, we have A dotted B, assuming that A and B are not like the 0 vectors. So A and B are always going to be positive values, right? and you have positive values, and then you have the cosine of the angle is 0. So that would, the only time this thing would equal to 0, the A dot B would equal to 0, is that if cosine of theta is equal to 0, and that's only going to happen when the angle is equal to pi over 2. So that's going to be an important fact for us to remember, and it's one of the most useful facts that this dot product can give us. Because later on we will be looking at orthogonal properties or perpendicular. Orthogonal, by the way, means perpendicular. You guys get that? All right. Dot product has a bunch of other properties in relation to some addition, subtraction, and some of the basic things that we learned in algebra, like distributive properties and stuff. So we can think about the dot product as some sort of multiplication. And so we can have some combinations of multiplication and addition to see how things work. Number one, let's take a look at number one. Oh, wait a minute. I want to change my scalar. I know they have arrows and stuff, but just to make it absolutely clear, let's change the scalar to something else. Alpha. Let's change that scalar. All right, so let's take a look at this one by one, and let's justify them, kind of like, almost like proving them. So if we take a look at A dot A, for example, we can assume that A, vector A, is equal to, let's go to 3D for this as an example, A1, comma, A2, comma, A3. And so let's actually perform the A dot A, the dot product. A dot A is equal to, well, no more signs here, A1 times A1 plus A2 times A2 plus A3 times A3. And if you look at the definition of the magnitude, it's just the square root of this thing, right? So the magnitude is essentially the square root of A1 squared plus A2 squared plus A3 squared. And so the difference between these two expressions is that if I just square this one, then I would get the, if I would square the magnitude, then I would get an equality from the other side. So it turns out that A dot A is in fact equal to the magnitude of A squared. So that little fact will come in handy sometime later on this semester. It'll help us prove some things when we start taking derivatives of things with vectors. So we have these other properties, like you can switch the order. What's that called when you can switch the order or something? Commutative. So we've always taken commutative for granted when we're adding and multiplying, but you know, we take a look at it a little bit more carefully when we're subtracting, because subtraction is not commutative, and neither is division. And it turns out that one of our other vector multiplications, our vector product, will not be commutative, interestingly enough. This idea of distributing, with the dot product, you can distribute over addition. This one is not quite that other property because this combines scalar multiplication with a dot product. And here's where I guess we should really point out the idea that the scalar product, the dot product, results in a scalar. And so when you take a dot of something, then your answer is going to be a scalar. So let me put one property that looks like it might be missing, but it actually doesn't work. A dot B dotted with C is equal to A dotted with B dotted with C. So we kind of know this as an associative property. We don't want to abbreviate. Right. So that's what I'm saying, is that this is not a property. So this is not a property because it doesn't make sense. And why doesn't it make sense? It doesn't make sense because when you take the dot of A and B, you're going to get a scalar, and now this is really a scalar multiplication. So a scalar times, this is no longer a dot product, not dot. It's not a dot product anymore. So this thing doesn't make sense. So it turns out that we have to be really careful about how we come up with these properties. Some properties that seem like they've been obvious because we've been dealing with real numbers all this time. It seems like they've been obvious the whole time. Now when you start dealing with vectors, you're playing with a new set of rules. So this other symbol over here, so this is, again, number 4 is not quite an associative property because you're doing scalar multiplication and dot products. And if you look at each of these values, you know that the result is going to be a scalar. And you can see how each of these within the parentheses would simplify. Okay, the last one, 0 times, this is like your 0 vector. Everything goes to 0 when you multiply by 0. But it is important to point out that for this one, that this 0 with an arrow on it does make a difference. 0 with an arrow on it means it's a 0 vector. Or you can think about that as the origin. That's different from, say, the result that you get if the two vectors are perpendicular and you get 0. This is a 0 scalar. And so there will be times where it would be really important to distinguish between a 0 scalar and a 0 vector. A lot of times it's just 0, so it doesn't make a difference. But for the purposes of the math that we might need to do, it might make a difference that you're dealing with a 0 vector versus dealing with a 0 scalar. Okay? So, technically, I think the whole question about the 0, the dot product being equal to 0, they're looking at A and B have to be non-zero vectors. Because otherwise, you can't, yeah, I mean, it's true. You can say that technically or mathematically the 0 vector is perpendicular to any vector. But you can't really see that geometrically. It's just there as an algebraic property. All right? So I did this really simple proof. If you look at the book, they might have proven 2 or 3 or 4. I think it might be good to know how to prove them. And you would prove them by just saying let A equal to A1, A2, A3. And then if you have a B, let B equal to B1, B2, B3. And then go through the process of dotting it and switching the order and dotting it to make sure that it's going to be all the same. Okay? Because I'm not sure if I'm going to ask you for a proof during the exam. But just in case, you should, be ready. So this is a simple proof, this little bit over here. This is a proof of an easy property. And I think 2 and 3 and 4, they're just as easy. I think all of these are fairly easy. And the process is to just let your A vector to be A1, A2, A3, etc. And then you'll walk through the computations and it'll be okay. All right, projection. So one of the important applications of the dot product is the idea of being able to project something onto something else. And in the book, they define 2 types of projection. One of them is a scalar projection. The other one is a vector projection. And don't know if you can guess what that means, but I think this is the notation that they use in the book. COMP for component projection, and PROJ for projection. The component projection gives you the component, which is really the length. That's a scalar projection. It gives you the length of the projection. So the whole idea behind a projection is that if you're projecting A onto B, then the projection is like shining a flashlight on top of vector A and seeing what the shadow is on B perpendicularly. And the component projection itself is the length of that shadow. So the length is a number. That's why they call it a scalar projection. On the other hand, a vector projection is an actual vector and that's the shadow that it makes. So you look at the shadow that it makes and you make a vector that's running along B. So running along B. So I want a vector of a specific length going in the same direction as B. Isn't that like a problem that we talked about earlier in this class? What? Unit vectors, right? So there's some unit vector involved here. So it turns out that if I know the length, and then I want B to be going, I want this new vector to be going in the direction of B, I could just take this length, A dot B, divided by the magnitude of B. This is just the length, right? And then I want it going in the direction of B. So B, if it's a unit vector, great. If it's not a unit vector, I have to, what's that word called again? Normalize. I have to normalize B. How do I normalize B? Divide by its magnitude. So what we're saying is that if I want the vector in the same direction as B, but I want it to have this component length, then this is what I would do. I would multiply by the component, and I would take the vector B and normalize it. Well, that's exactly what this is. Can you see it? The magnitude of b is squared in the denominator, right? So it's like taking one of those magnitudes of b and putting it under the b. It's the same thing. Okay? So there should be some examples in your homework. This idea will be important for us to find distances of things. If we're finding a distance from one point to another, and the other things is like a plane or a line, then this whole idea of a vertical distance or a perpendicular distance is important, because a projection gives us this perpendicular drop from one vector to the other. All right, now the rest of the topic is physics, and I don't want to talk about physics. You guys still have to do homework on physics, so good luck.
There's one with a plane and moving in a certain direction, and there's a man flying in another direction. And
Yeah. So that's just the plane. The plane problem is just addition. Addition and subtraction of vectors and stuff. Yeah, and so the angles, the whole, north 45 west, it just means, if you draw the north, west, east, south in your XY plane, and the 45 degrees just means you're going to drop 45 degrees. So you're looking at y equals an x line or something. Vector 1, 1, negative 1, 1, 1, negative 1, or something like that. All right, good luck with that.